Hello, and welcome to section 1.6 of our linear algebra lecture notes. Today we're going to talk about applications of linear systems, and we'll do one specific example. So in general, if you want to apply some of the techniques we've learned so far to solving real-world problems, the first step is you need to identify any unknown quantities in your situation and label them with variables. And you should always try to use variables that make sense in your situation. If you have like something that has a name, you can use a letter to represent that. If something comes in some concrete order, maybe you can make it x1 through xn, that sort of thing. Also, then you want to write equations to represent all information. And even if you end up with more information than you need, more info is better than less. And especially as we've seen in row reducing matrices, if we have extraneous information, it usually ends up getting filtered out to be a row of zeros anyway. So it won't really hurt anything if you have a little bit more information than you need. Next, we want to, sort of make sure that linear algebra does apply here. And so before we create an augmented matrix, make sure that your equations are linear. So if you have exponents, then you know you're going to need a different method. And now we want to use row reduction to get a reduced echelon form matrix. So we already know how to do this, but one thing to bear in mind is if you just need to know whether there is a solution. So if you just need to know if a solution exists, then you just need echelon form rather than reduced echelon form. Most of the examples we'll see in this section do require an actual solution, but there are plenty of real-world situations where you just want to know, like, can I do this? Even if you don't necessarily need to know how to do it. And our example will talk about balancing chemical equations. So you might have a situation where you try to balance something and there's no solution, and that actually means that that reaction can't happen. Okay, so write your solutions in the appropriate format. So you might want vectors, you might want parametric, kind of figure out in your context. And then kind of relating to that, once you put it back into your original context, you want to pay attention to your units and you want to check to make sure that what you got makes sense. So both mathematically and concretely, if you're asking for a quantity, you shouldn't have a negative number because you can't have, -5 pencils in. I mean, I guess technically you can if you say, well, I gave away 5 pencils or something like that. But even in that situation, if you have a negative number, you want to make sure that it would make sense to have a negative number for your situation. Okay, so let's put this into action. We have the Alka-Seltzer chemical equation. So if you've ever had an upset stomach and taken Alka-Seltzer, it's a little tiny disc, and you stick it in water, and when it dissolves, it makes a nice little fizzy thing, and then you drink it, and it makes your stomach ache go away. So what we want to do is we want to, first of all, identify our situation, and we need some, and this is kind of interesting in terms of variables, because when you first look at this situation, you might think that the different atoms are the things that we want to have as our variables. But actually, those are things that we know. We know how many atoms of, I guess the Na is sodium, and then H is hydrogen, C is carbon, and O is oxygen. So we actually know how many of those we have, and what we want to know is the number of each molecule. So in fact, what we should do, I guess, before we even write down anything with our atoms, is we want to label, we want X1 of our first molecule, x2 copies of our second molecule, x3 of our third, x4 of our fifth, and x5 of our fifth. So we don't know how many carbon dioxides are present in our reaction, and that's the information we want to know. And so in order to now kind of generate our information, well, first of all, we need a vector corresponding to each molecule. So the atoms that might be present are sodium, in this particular situation, sodium, hydrogen, carbon, and oxygen. And so I will start by writing down the vector for sodium bicarbonate. I need to remember to stop myself and let you enter the sodium citrate in your quiz. So first of all, when we look at sodium bicarbonate, so that's this very first molecule here. So because the Na just has no coefficient down, no subscript down below, that means there's only one of those atoms. And same thing with the hydrogen and the carbon, but the oxygen, because it has this little subscript of 3, that means we want 3, we have 3 atoms of oxygen in every sodium bicarbonate molecule. And then similarly for, I guess, citric acid, this time, well, first we have H3, but then we also have H5. So it turns out that hydrogen has 8 atoms in citric acid, has 8 atoms of hydrogen in it. And so you find the row that you use to correspond to hydrogen and fill that in with an 8. We don't see any sodium, so we just put 0 there. And then let's see, we do have carbon. We have a subscript of 6. So for the carbon row, we put 6, and oxygen, we have 7. Okay, so the next one is, for our quiz, we'll do the sodium citrate. And what I want you to put in order is the number of atoms of each type. And just remember, these are not written in the order that we wrote them over here. So it does have our sodium first, but then hydrogen is not listed second. So make sure you reorder those so that you have the sodium, then the hydrogen, then the carbon, and then the oxygen. And separate it by commas to make sure that it's recognized by the quiz format. Okay, so I'm going to go ahead and fill in the answer to the quiz, and hopefully you got these correct. So the sodium, we have 3 molecules, hydrogen, it looks like we have 5, carbon 6, and oxygen 7. So hopefully you all got that correct, and if not, maybe go back and look at the earlier ones and make sure you understand that, or reach out to me and I'm happy to help you anytime. And that always is true, by the way. Okay, so sodium, we have 0 atoms. For water, H2O, we have 2 oxygen and 2 hydrogen and 1 oxygen. And then finally, carbon dioxide, we have 1 carbon, 2 oxygen, and no sodium or hydrogen. Okay, so now we're ready to move on. Now we've got vectors, which is nice, and we need some linear algebra. Well, I'm actually going to write my vector equation up here. So remember, we saw that we wanted x1 times our sodium bicarbonate plus x2 times our citric acid. And then that's going to put out x3 times our sodium citrate. Oh, and I meant to write this down. This is sodium citrate. And then we also have water and carbon dioxide. Okay, so we have x3 times our sodium citrate plus x4 times our water plus x5 times our carbon dioxide. So that's our vector equation. And now we want to use row reduction. And you might say, well, usually we're used to having a system of equations that's equal to something. But here's what we can do to make this into a system that has all our variables on one side. Well, the x1 and the x2 stay where they are, but then the x3, x4, and x5, we can move them to the left-hand side of the equation by simply subtracting them out. And we're going to need to do that in order to apply our linear algebra techniques, because we want all of our variables on the left. And once we've moved everything to the left, we have nothing left on the right-hand side, which is our zero vector. So now when we do row reduction, we could stick that zero vector in there, but it's not going to change anything. So a lot of times we just leave it out and row reduce the coefficient matrix. If you have a non-homogeneous equation, you're not allowed to do that, because you every time you row reduce, you change things in your on your right-hand side. Whereas if you just have zeros, no matter how you add and multiply them, you're not going to change the values that are zero. Notice that as I'm filling in this equation, I'm putting negative signs by all the things that are multiplied by our negative variables. And that's because I'm just moving that negative sign from the x5 to the vector. I could do that for each of these. Maybe I should have to make it clearer. Okay, so now we are going to use GeoGebra, which we've already seen is kind of a handy way to row reduce now that we're solid at row reduction. Although I will encourage you, if you don't feel solid with your row reduction yet, to definitely get some practice. I just don't want you to have to watch me practice that on this video, since we've already done a lot of that on previous videos. And I think GeoGebra will give you these answers with decimals rather than the negative 1/3, but that's okay. And so this might look confusing to you, like especially the negative signs, but let's remember that this is an augmented matrix with zeros on the right. And each of these columns corresponds to one of these variables, even the column that has the negatives in it. And so that very first row, for instance, corresponds to the equation x1 minus x5 equals 0. And the second row corresponds to x2 minus 1/3 x5 equals 0. Then we have x3 minus 1/3 x5 equals 0, and x4 minus x5 equals 0. So we have x1 equals x5, x2 equals x5 divided by 3, and so on. x3 equals 1/3 times x5, and x4 equals x5. And so here we have a free variable, which might seem kind of weird at first. So x5 is our free variable. But that's okay, because what this is really telling us is that we can choose how many molecules of carbon dioxide we want to put in, and then that will tell us, because remember the x5 corresponds to the carbon dioxide molecules, that will tell us how many molecules of the other pieces are going to go in here. And so let's pick, just to make a nice even number, let's let x5 equals 3. But we could let it equal something else. Then what we can do is, now we know that x1 is equal to x5. So that's 3 times, let's see, I can't quite see my original equation. Okay, so we have 3 times our sodium bicarbonate plus our citric acid is 1/3 of x5, so we don't have to do anything there. And then our sodium citrate is also 1/3 times our carbon dioxides. Okay, and then our oxygen is actually equal to our carbon dioxide, and then of course our number of carbon dioxide we chose to be 3. So here is our final equation. I'm worried that you can't see that blue so well. Let me change its color. Let's make that. Okay. So now what I want you guys to do for your last quiz is to go ahead and balance the chemical equation given here, and you're using the same process that you used before. And what we're going to do is say, once you're done, you'll get a kind of a similar type of result, and we'll choose 3 to be the number of H2S molecules, and then I will be asking you how many oxygen molecules there will be.